Hi students, in this session we are going to see the topic trigonometric Fourier series. Trigonometric Fourier series. So we all know in a trigonometric Fourier series the orthogonal functions are trigonometric functions. In trigonometric Fourier series the orthogonal functions are trigonometric functions. So here the trigonometric functions are nothing but sine function and cosine function. That means in trigonometric series we will get sines and cosines. Okay, or simply we can say it is in terms of infinite sum of sines and cosines. This trigonometric Fourier series is in terms of infinite sum of sines and cosines. So we all know that. So we will see the proof of that one. So how it forms the infinite sum of sines and cosines means we all know that sine n omega naught t sine m omega naught t are orthogonal to each other. These two are orthogonal to each other over the period, over the time interval t0 to t0 plus 2 pi by omega naught. So we all know this. That is, these two signals are orthogonal to each other over the interval t0 to t0 plus 2 pi by omega naught. Okay, and we all know 2 pi by omega naught is nothing but t. So we all know that t equal to 2 pi by omega naught. So simply we can write the integral as t0 to t0 plus capital T. So you can write this one or this one. Or if you want to simplify somewhat, if the starting time is 0, that is t0 equal to 0. 0 to 0 plus capital T, that is capital T. So you can write like this also, 0 to capital T. Because if t0 equal to 0, then I can write 0 to capital T. Okay. So in this tree you can use anything. So if you want to use simply, you can go for this one. Okay. So for better understanding, I am going to represent this in this equation. So I am taking the limits from t0 to t0 plus capital T. Okay. In this derivation, I will take these limits, but you can take 0 to 2 also. There the t0 value is 0. Okay. For perfect explanation, I am taking this one. Okay. In my explanation. Now, so these two are orthogonal over the interval t0 to t0 plus capital T. That is t n equal to 1 sine 1 omega naught t and m equal to 2 sine 2 omega naught t. Okay, so this will form an orthogonal set. So along with this, if you have sine 3 omega naught t or sine 4 omega naught t, so they will form an orthogonal set because all these functions are orthogonal to each other. But this set, the set that is sine omega naught t, sine 2 omega naught t, sine 3 omega naught t, sine 4 omega naught t cannot form a complete set. Why? Because there are the terms, cosine terms, which are also orthogonal to these sine terms. There are terms like cosine terms which are also orthogonal to sine terms. A complete set is the one where in that set there will be existence of no other set which is orthogonal to the signals present in that one. Here, if you want to say this as a complete set, there should not exist any other signal which is orthogonal to this one. But in this case, there are cos terms or cos functions, cosine functions, which are orthogonal to sine functions. So this set will be a complete set. This set will be a complete set only if we include cos terms into this set. Only if we include cos terms into this set, then only we can say this as a complete set. That means we have to add cos terms also. That is, we have to add cos 1 omega naught t, cos 2 omega naught t, cos 3 omega naught t, and so on. If we add all these cos terms in this set, then this will become as a complete set. Then I can represent a function x of t using this complete orthogonal function that I explained in the orthogonal signal space concept. Okay, so to make it a complete set, I have to combine both sines and cosines. I have to consider both sines and cosines. So now the complete set is The complete set is sine n omega naught t, sine n omega naught t, and cos n omega naught t, sine n omega naught t, and cos n omega naught t. So this is a complete set. It will form a complete set where n equal to 0, 1, 2, 3, and so on. Take like this. So what are the signals that I can get in this complete set? This will be a complete set. Now what are the elements that are present in this complete set are sine terms and cos terms. That is sine 0 omega naught t, sine 1 omega naught t, sine 2 omega naught t, sine 3 omega naught t, and sine n omega naught t. In the same way, we have cos 0 omega naught t, cos 1 omega naught t, cos 2 omega naught t, cos 3 omega naught t, and cos n omega naught t. So we have so many terms in this set which will form a complete set. Why? Because in the set, each and every function is orthogonal. That is, they are mutually orthogonal functions. So this will form a complete set. Now I can represent a function x of t. X of t can be represented by using this complete orthogonal set, complete closed orthogonal set over the interval t0 to t0 plus t by. So now I am going to represent this signal. So how can I represent? Simple. We have to consider the linear combination. We have to consider the linear combination of all the functions present in this set. We have to consider linear combination. So before going to linear combination, first of all you have to know what are the functions that are present in this complete set. Now we will see the complete functions that are present in this set. So in that complete set, the functions are, first I am starting with cos terms and then I will write the sine terms. So first I will start with cos terms. Cos 0 omega naught t. Okay. Cos 0 omega naught t. Next, cos 1 omega naught t, cos 2 omega naught t, and so on. Cos n omega naught t, and so on. In the same way, we have sine terms also. Sine 0 omega naught t, sine 1 omega naught t, sine 2 omega naught t, and so on. Sine n omega naught t, and so on. So these are all the elements or the functions that are present in that complete set. Now I can represent a function x of t. Function x of t over the interval t0 to t0 plus capital T by using this our complete orthogonal set, because all these functions are orthogonal over the interval t0 to t0 plus t. That is, these all signals are mutually orthogonal. So how can you represent? We will represent by considering the linear combination of all these functions, by considering the linear combination of all the functions present in this complete set. So what is linear combination? We all know that. So how can we get the linear combination? We get the linear combination just by multiplying each function in the set with a constant and adding all the functions. So each function should be multiplied with a constant. This will be multiplied with a constant, this will be multiplied with a constant, this will be multiplied with a constant, and that will be multiplied. And we have to add all the functions. Then I get the linear combination. By using that, I can represent a function x of t. Now see, so now I am representing a function x of t, a periodic function x of t over the interval t0 to t0 plus t by taking the linear combination of the mutually orthogonal functions. That is, by using the complete orthogonal set. Okay, using the concept of orthogonal signal space as x of t will be equal to linear combination of all these things. Starting with this. So here I will take a constant. So for cos I will take the constant as a, and for sines I will take the constant as b. Okay. So see, for cos I am taking the constant as a. So what happens? So inside this there is A. Here also A. But we have to go for different constants. For that reason, for A, here the n value is 0. So here we get A0. Here n value is 1, A1. N value is 2, A2. N value is n, An. Like that. That means now the linear combination will be equal to first one. A0 cos 0 omega naught t, and plus we have to add everything. So we have to multiply each function with a constant and then we have to add. I am doing the both at the same time. Plus A1 cos 1 omega naught t plus A2 cos 2 omega naught t plus so on, plus An cos n omega naught t plus so on, plus B0 sin 0 omega naught t plus B1 sin 1 omega naught t plus B2 sin 2 omega naught t plus so on, plus Bn sin n omega naught t plus so on. Clear? So this is the representation of a signal or function x of t over the interval t0 to t0 plus t by using the complete orthogonal set. That is by taking the linear combination of mutually orthogonal functions. Like this, by taking the linear combination of mutually orthogonal functions. So we have to simplify this. So how will you simplify this? See, cos 0, because 0 into anything is 0, so cos 0 is 1, 1 into a0 is a0. So here I have to write a0 plus this one a1 cos omega naught t plus a2 cos 2 omega naught t plus so on, plus an cos n omega naught t plus see, sin 0 into anything is 0, sin 0 is 0, 0 into b0 is 0, 0 into b0 is 0. So there is no need to write this b0 term, because b0 into sin 0 is 0, 0 into b0 is 0. So no need to write. So you can write directly b1 sin omega naught t plus b2 sin 2 omega naught t plus so on plus bn sin n omega naught t plus so on. So this is the a little bit, because here we get only a naught and here we get 0, and we have to simplify this. I will write in a short form by using the notation summation. See, first of all I can take summation. Here n term is a0, a1, a2, a3, an and so on. So n is from 0 to infinity. After n also we have some n plus 1, n plus 2, n plus 3 up to infinity. So the n value is from 0 to infinity. So in this case, see, b1, b2, b3 and so on. So there is no 0. So we no need to write the n value of 0. That is, here the n value is from b1. N value is from 1 to infinity. So for that reason, I am simply writing, first I am writing a0. Separate one. Plus summation. See, here value is 1 to infinity. Here also the n value is from 1 to infinity. So I am writing as n equal to 1 to infinity. So here the terms are an cos n omega naught t, plus So if you write n cos n omega t, what will you get? First n equal to 1, a1 cos 1 omega naught t, n equal to 2, a2 cos 2 omega naught t, n equal to 3, a3 cos 3 omega naught 3, n equal to n, an cos n omega naught t, and then also we will get up to infinity terms. Plus, on the below side is we have to write bn, right? bn, because n value is from 1 to infinity, so b1, b2, b3, bn and b infinity. So bn sin n omega naught t, sin n omega naught t. So this is the equation for x of t. This is the equation for x of t. So x of t equal to a naught plus summation n equal to 1 to infinity an cos n omega naught t plus bn sin n omega naught t. See, we have only the value of a naught. We doesn't have the value of b naught. Why? Because b naught means sin 0. Sin 0 is 0. 0 to b naught is 0. So this term will be equal to 0. So there is no b naught. We have only the term of a naught. Hence, in the a naught as separate one. And from 1 to infinity we have for a1, a2, a3 as well as b1, b2, b1, b2, b3. For that reason, I have gone for the summation from n equal to 1 to infinity an cos n omega naught t plus bn sin omega naught t. See, it is in terms of infinite sum of cos and sine terms. Cos and sine terms. If the series is in terms of infinite sum of cos and sines, then it will be called as trigonometric Fourier series. So this equation represents the trigonometric Fourier series. Trigonometric Fourier series. So this equation, that is x of t equal to a naught plus summation n equal to 1 to infinity an cos n omega naught t plus bn sin n omega naught t will represent the trigonometric Fourier series. So this is the trigonometric Fourier series, a representation of a continuous time period signal x of t. This equation is the trigonometric Fourier series representation of a continuous time period signal x of t. Why? Because it is in terms of infinite sum of sines and cosines. So we will call it as a trigonometric Fourier series. And now we have to derive the constant in this equation. That is, we have to derive the equation of a naught, an and bn. So we will go in the next, we will go for deriving these values of a naught, an, bn. So those values will be derived from the concept of orthogonality. From the concept of orthogonality, we will derive the values of a naught, an, bn. Okay. Now we all know that this is the trigonometric Fourier series representation of a continuous time periodic signal. In this, we have to find out the trigonometric Fourier series coefficients. Trigonometric Fourier series coefficients. So here the coefficients are a naught, an, bn. So we have to find the values of this a naught, an and bn. We have to find these values. Now we will derive the values of a naught, an, bn. Those are nothing but the trigonometric Fourier series coefficients. Because this approximation, this trigonometric Fourier series representation is mainly dependent on these coefficients. So if you know the exact values of a naught, an and bn, then we can perfectly represent this x of t. So the main this Fourier series, trigonometric Fourier series representation is dependent on the coefficient, that is a naught, an and bn. So we have to find out the values of this a naught, an and bn. Now we will find out this. So first, before finding that, I am again writing the equation, the trigonometric Fourier series representation of a continuous time periodic signal x of t. So that will be equal to x of t equal to a naught plus summation n equal to 1 to infinity an cos n omega naught t plus bn sin n omega naught t. Okay. In this, I have to find out the values of a naught, an, bn. To find out these values, I will use the orthogonality condition, or simply first analogy between vectors and signals. In that, I explained you one thing. How can you represent one signal in terms of another signal? If there are two signals, x1 of t and x2 of t. How can you represent one signal in terms of another signal, or one function in terms of another function? Simply x1 of t is approximately equal to c12 into x2 of t. If you want to write it perfectly, x1 of t equal to c12 into x2 of t plus xc of t. If the xc of t value is very very small or equal to 0, then x1 of t is equal to c12 into x2 of t. Here all of you know the value of c12. How can you get that c12? Here all of you know the value of c12. c12 equal to integral. So limits 0 to t. So for the given interval, whatever the interval, we have to apply those intervals. So here the interval is t0 to t0 plus capital T. So you can write that, apply the limits as used. So integration of the product of the signals, that is x1 of t, x2 of t dt by integral second signal x2 square of t dt. We all know the value of, so we all know this value of c12 because I derived this equation. So we all know that c12 will be equal to integral x1 of t, x2 of t dt by integral x2 square of t dt over the given interval. Now I use this concept for simply finding the values of a0, an and bn. Just to get the a0, an and bn, if we use this, I can simply get this. Okay, so there is no need to go for long process. We have the long process also. So with the long process, by taking some terms on both sides and some integrals on both sides and performing and simplifying the equations, I will get the values of this a0, an, bn. So without all this, just by using this concept, without all those, just by using this concept, I can directly find out these values of a0, an and bn. So see how. First, in this, I am separating this. So if I separate this first one, I will get a0 a separate one. Next, summation n equal to 1 to infinity an cos n omega naught t, second one. And third one, summation n equal to 1 to infinity bn sin n omega naught t, third one. If we make it as three separate things, first I will go for the derivation of the first one, a0. First I will find out a0. So how will you find out a0? Simply here, while finding a0, leave these two. We consider only a0. Consider like this, as x of t equal to a0, some constant. If there is nothing, we can write as 1. a0 into 1. Treat these are one signal, and this one as another signal, and a0 as constant. a0 as constant, like this. So here x1 of t is x of t, and c12 equal to a0, and x2 of t equal to 1, because a0 into 1 is a0. So I am considering this one because I have to find out the value of a0 only. So I am leaving these two and considering this as x of t equal to a0, or approximately x of t is approximately equal to a0 into 1. X of t is the first signal and 1 is the second signal. So I need the constant c12. Now what is the formula for c12? c12 is integral x1 of t, x2 of t dt by integral x2 square of t dt over the given intervals. The same way, here I need the a0. So a0 value will be equal to integral. Here the limits are t0 to t0 plus capital T. Or if you want to write it simply, you can write 0 to t. 0 to capital T. This is also same. If t0 equal to 0, what happens? 0 to 0 plus capital T is capital T. 0 to capital T. a0 equal to t0 plus capital T. First thing. Next, what do you write? x1 of t. So here the x1 of t is x of t. Into x2 of t. x2 of t is 1. x2 of t is 1. So here to write 1. Next, dt. Divided by integral t0 to t0 plus capital T, x2 square of t, x2 square, that is 1 square. That is 1 square because x2 of t is 1. So 1 square dt. 1 square dt. So that will be equal to, see, x of t into 1 is x of t. So we can write as integral t0 to t naught plus t x of t dt. X of t dt divided by see, 1 square means 1. So integral t0 to t naught plus t 1 dt. T naught plus t 1 dt. That means, so integral t0 to t naught plus t 1 dt will be equal to t with limits t0 to t0 plus capital T. That will be equal to, first substitute this one, t0 plus capital T minus t0 plus t0 minus t0 get cancelled. That will be equal to capital T. So the answer of this, the integration t0 to t0 plus capital T 1 square dt will be equal to t. So you can write as t. Okay. So simply the equation for a0. So how can you write? Simply the equation for a0 will be equal to 1 by t. So I am taking 1 by t integral t0 to t0 plus capital T into x of t dt. So this will be the value of a0. So you can find out the value of a0 like this. So this one. So this is the value of our a0. So a0 will be equal to 1 by t integral g 1 by t integral t0 to t0 plus capital T x of t dt. Okay. So this is the first one. In the same way, you have to find out the next one also. You have to find out the next one. Okay. So you all know first one, a0 will be equal to 1 by t integral t0 to t0 plus capital T x of t dt. This is the first one. Second, we have to go for second one. See. So for second one, what I have to consider? I have to consider the second thing. That is summation n equal to 1 to infinity a n cos n omega naught t. Means here n value is from 1 to infinity. So leave this. So you have to consider a n cos n omega naught t. To find out the value of a n, I will consider this one and I will leave a naught and b n sin omega naught t. While finding a naught, I left these two. So while finding a n, I will consider only this term a n cos n omega naught t, this term, and I will leave a naught and I will leave b n sin omega naught t along with summation n equal to 1 to infinity. I will consider only this thing. Okay. So by considering this thing and using this formula, I can find the value of a n. See how will you find that value? Okay. So I hope you are clear with this one. Now I will find out the value of a n. So to find the value of a n, I will consider second term only. So here I have to consider x of t. X of t will be equal to a n cos n omega naught t. So I will consider like this. And compare this with this equation. Here x1 of t will be equal to x of t and c12 will be equal to a n and x2 of t equal to cos n omega naught t. Okay, now compare these two. So in this I have to find out the value of a n. So using this equation I will find out the value of a n. How can you get the value of a n? A n will be equal to see integral limits t0 to t0 plus capital T, t0 to t0 plus capital T. So first what I write x1 of t. So x1 of t is x of t into x2 of t. x2 of t is cos n omega naught t. So x2 of t is cos n omega naught t dt by integral t0 to t0 plus t x2 square of t. So x2 of t is cos n omega naught t. So x2 square cos square n omega naught t dt. Cos square n omega naught t dt. Okay, simple. I am comparing this equation with that one. That is x1 of t equal to x of t. C12 will be equal to a n and x2 of t will be equal to cos n omega naught t. So in this, the value of C12 is this one. So in the same way, in this, the value of an will be equal to this one. So integration of x of t into cos n omega naught t dt by integration of cos square n omega naught t dt over the interval, that is t naught to t naught plus capital T. Here, if we simplify this one over the limits t naught to t naught plus t, what you get? So here you get the answer as t by 2. Here you get the answer as t by 2 for this. So that is here integral t naught to t naught plus capital T cos square and omega naught t dt will be equal to capital T by 2, will be equal to capital T by 2. So that is for your work. If you go on solving this equation, you will directly get as T by 2. So we will substitute the value of this one as T by 2 in this equation. So what we can write, we know that this one. So the value of an, I need the value of an. Here an will be equal to integral t naught to t naught plus capital T x of t cos n omega naught t dt, cos n omega naught t dt whole divided by the value is t by 2, because this value is equal to t by 2. So that is finally equal to, so if you go to upside, we will get 2 by t integral t naught to t naught plus capital T x of t cos n omega naught t dt. So this is the value of an. So an will be equal to 2 by t integral t naught to t naught plus capital T x of t cos n omega naught t dt, cos n omega naught t dt. So this is the equation for an. In the same way, I can find out the equation for bn also. So simply, see, in this equation, what I have to consider? I have to consider third one, that is bn sin omega naught t, and I have to leave the first two. Because I have to find out only bn. So see, to find the bn, I have to consider x of t is approximately equal to bn sin n omega naught t, and I compare that with this one. Okay, that is x1 of t equal to x of t, c12 equal to bn, and x2 of t equal to sin n omega naught t. So I have to find out the constant bn, that is here c12, there bn. So what happens? Bn, in place of a I get bn, that will be equal to integral t naught to t naught plus t x of t. Here I will get sin n omega naught t, because in this we have sin n omega naught t dt by integral t naught to t naught plus t sin square n omega naught t dt. Come to this side. So integral t naught to t naught plus t sin square n omega naught t dt, because here we will get sin square n omega naught t dt. That value will also be equal to t by 2. So finally what we get? Bn value as, so finally we can get bn equal to integral t naught to t naught plus t x of t sin n omega naught t dt by t by 2. So finally if we do as the same, so for the third one, that is here we have to consider x of t equal to bn sin n omega naught t. Okay, and compare this with this one. After that we have to find out c12, that is bn. So the value of bn will be equal to 2 by t. If you go as I did for cos, bn equal to 2 by t integral 0 to t naught to t naught plus capital T x of t sin n omega naught t dt. So this is the equation for bn. So here I got the value of an, here I got the value of bn. Already I find the value of a naught. So what is the value of a naught? A naught equal to 1 by t integral t naught to t naught plus t x of t dt. So these are the values of a0 and an and bn. So these are the trigonometric Fourier series coefficients derivation. So here I derived the values of a0, an and bn just by using the concepts of C12 where I explained in orthogonality. So orthogonality concept I explained when I gone for the analogy between vectors and signals. I explained you x1 of t is approximately equal to C12 into x2 of t, and C12 value is this one. By using this I directly find out the value of a0 in the first one, and here I find the value of an, and after that you have to do this bn. I explained you everything. So do the same what I did for an, do the same, then you get the value of bn as 2 by t into integral t0 to t0 plus t x of t sin n omega naught t dt. So remember these three are very very important. First one, second one, first one, second one, and third one. So this is the value of a0, and this is the value of an, and this is the value of bn. Remember these three things. These three are the trigonometric Fourier series coefficients values. Okay. So I will go for the summary of this class. So in this class I explained you about the trigonometric Fourier series. So trigonometric Fourier series is in terms of infinite sum of sines and cosines. So I consider a complete set of orthogonal functions in sines and cosines. Using that I gone for the representation of a function x of t by linear combination of all those signals. Okay. So I had gone for the linear combination. From that I got the trigonometric Fourier series expression for an continuous time period given as x of t equal to a0 plus summation n equal to 1 to infinity an cos n omega naught t plus bn sin n omega naught t. So after this I gone for the derivation of each and every one using these concepts. So I used these concepts and find the values of a0 as 1 by t integral t0 to t0 plus t x of t dt, and an as 2 by t into integral t0 to t0 plus t x of t cos n omega naught t dt, and bn as 2 by t into integral t0 to t0 plus t x of t sin n omega naught t dt. So this is today's class. In next class we will go for the exponential Fourier series. So we will go for the representation of an exponential Fourier series and deriving the exponential Fourier series coefficients. Okay. Thank you one and all.